Okay, so in this lesson, we are talking about relations, which are just a relationship between two variables, let's say x and y, often referred to as the independent and dependent variables. And we're talking about what it means to be a function. So a function by definition means that we have two sets, set A and set B, and each element in set A must have exactly or correspond to exactly one value in set B. So if we look at these two examples, or this example down here, we have A and B, let's say, for these two sets. Notice we have 75 maps to C, for instance, and 95 maps to A. However, 94 also maps to A. So let's think about that for a second. The statement says each element in A must be assigned to exactly one value in B. Well, 95 only goes to one value, and 94 only goes to one value. It just happens to be the same value. So this is, in fact, a function. Now, what we can't have, let's say, is if we had another number over here like 22, and let's say that, or sorry, not over there. We need it on the other side. Let's say we have another thing over here. So let's see, we're at, say E. So let's say 95 went to A and 95 also went to E. So now 95 goes to two values in set B. Then this would not be a function. Okay. And the little paragraph here says to consider this or a function to be like a machine, right? You put something in, you get something out. And you can only get a certain thing. You can only put certain things in and get certain values out. Those are going to be what we call our domain and range. So the domain are going to be our values of x, and our range is going to be our values of y. And they're going to be the things that they are allowed to be. All right. So let's take a look at these first couple examples. It says determine if each relation is a function or not. If it's not a function, say why. Okay. So we have ordered pairs. We know that those are sets of x and y. Let's separate them just like above into two sections. So let's call this x, and in set x, we have 3, 2, 5, and 8. Okay. And in set y, what do we have? Well, we have 4, -1, 4, well, 4 we don't need to write twice, and 18. So 3 maps to 4, 2 maps to -1, 5 also maps to 4, and 8 to 18. Now, remember it said we have to have for every value in set A, or in this case set X, we can only have one value in set Y. Each one of the values of X only goes to one Y. So this is a function. Now let's see what the contrary would be. So in this next example, again, let's make two sets. Let's make a set X, and let's make a set Y. So in X, we have 7, 6, 7 again, so I'll leave that alone, and then 8. And then over here, I have 1, 4, 3, and 16. 7 maps to 1, 6 maps to 4, 7 maps also to 3, and then 8 to 16. So this time, in my set X, one of the numbers maps to two different numbers in the set Y, and therefore this is not a function. Another way to look at this is if you notice, we go back up here. Notice in our set X, we had more values than we had in our set Y, and that was okay. That's a function. But in this case, we have more values in our Y than we have in our X. That is not a function. So that's another way to look at it, right? And again, that's because a single X gives back two answers for Y. But for it to be a function, each X should only give one answer Y. Okay?